Retrosynthesis, also known as retrosynthetic analysis, is a method used in synthetic organic chemistry for planning the synthesis of complex organic compounds. The goal of retrosynthesis is to take a target molecule and disconnect it into simpler, more readily available starting materials. This process involves breaking the target molecule into smaller fragments and then thinking backwards to determine how the fragments could be synthesized. The result of the analysis is a proposed synthetic route that can be followed in the laboratory to synthesize the target molecule. Retrosynthesis is an important tool for organic chemists because it enables them to plan and design syntheses that are efficient, reliable, and safe. To make the ketone from the given alcohol, it should be obvious that the carbon atoms from two molecules of the alcohol will need to combine to give the 6-carbon product. This is going to require a carbon-to-carbon bond-forming reaction, which will most likely involve a Grignard addition to a carbonyl electrophile. Since ketones also react with Grignard reagents, we cannot make a ketone directly, so we must consider a detour via the related alcohol. This is considered a functional group into conversion which, in the forward direction, is easily achieved using PCC, PDC of sodium dichromate. This leads to the first significant disconnection of the carbon framework, in which the 6-carbon chain is broken into two 3-carbon fragments. One of these has to be the negative nucleophile, and the other piece has to be the positive electrophile. Placing a positive charge next to oxygen makes sense as that is the natural polarization based on electronegativities. The other fragment would then be negative, which matches the Grignard reagent. Once the Grignard reagent and aldehyde electrophile have been identified, their synthesis requires a short series of functional group interconversions, which may be related back to the given alcohol starting material. We have several choices of carbonyl-containing functional groups to choose from as the electrophile. However, most of them won't work in this situation. Recall that esters react with Grignard reagents in a sequence to give tertiary alcohols, and not the required secondary alcohol product. Carboxylic acids will quench the nucleophile, and acid chlorides react the same way as esters and over-alkylate. A ketone won't work either, since that would also result in a tertiary alcohol product. The best choice therefore is the aldehyde, which would react with the nucleophile to give the required carbon framework. The alcohol functional group will also be placed in the correct position for conversion to the ketone target molecule. Once we have decided that the electrophile synthon is actually an aldehyde, we need to assess how far we are from the alcohol provided as starting material. Since aldehydes are directly related to primary alcohols, we are one oxidation step away. Remember that primary alcohols may be converted to aldehydes using PCC or PDC under anhydrous conditions. For the nucleophile synthon, the negative carbon is provided by a Grignard reagent. This is available by adding magnesium to an alkyl bromide, so the bromide is the next precursor. Alkyl bromides are directly available from primary alcohols using PBr3, so we have completed the plan. For each step of the retrosynthetic scheme, remember to assess whether we have the chemistry needed to accomplish the forward conversion. Now we can put the target molecule together using the chemistry laid out in the plan. Using PBr3, a portion of the starting alcohol is converted to the alkyl bromide. This is isolated, purified, and characterized to prove its structure. The bromide is then mixed with magnesium in ether as solvent to give a solution of the Grignard reagent. In a separate flask, more of the starting alcohol is mixed with PCC to provide the aldehyde, which is also isolated, purified, and characterized. The aldehyde is then added to the Grignard solution, and the carbon-to-carbon bond-forming process ensues. Quenching that reaction with a suitable acid affords the secondary alcohol, which is isolated, purified, and characterized to check the success of the addition step. Finally, PCC converts the secondary alcohol to the target ketone and the process is complete.